Oh, hi, hello, and welcome to section number 6. Woo! More than halfway through. Slay. Um, but you'll have a test coming up sometime soon, right? Like, is the test already like next Thursday or is it the Thursday after? Sorry, I should know that. I don't mean that to be a jump scare. It's the Thursday after, right? Cool. So we have. Do we have actually any more new lectures, or is the second exam just 4, 5, and 6? I think just 4, 5, and 6 sounds right. But can anyone double check or refute that? I'm gonna go with it. Um, so, I mean, the first unit was kind of like, who are we? Where are we? What are we doing? What are amino acids? And then proteases. And then unit 2 so far has been, okay, there are these things called cofactors. Meet Miss ATP over here. Meet SAM over here. Meet NAD. Meet FAD. And we end off unit 2 with some of the more complicated FAD chemistry. So we only for class 5 and section 5 showed you the easiest FAD mechanism, but she gets up to some things. She has a really flourishing social life that's quite complicated. But we are going to break it down and hopefully make it feel less complicated. So we're going to do FAD today and talk about oxidases and monooxygenases. Before we do that, we're going to do a little review of some redox things, specifically with oxygen, like O2 redox oxidation levels. And then we do a kind of hard pivot into sugars. And really with that, I don't think that there's going to be a lot of like sugars on the exam, especially because it was just such a small part, like only a few pages there towards the end. But we will see that glucose metabolism and like glycolysis is really going to be putting into action a lot of the cofactors that we've learned now. So like canonically, about ATP, NAD, and FAD in metabolism. And so we're going to kind of get to like follow them to work and see their jobs and see how they function. And we're going to see they function very similarly to these kind of canonical examples that we've done. So we'll spend a little time at the end doing some sugar stuff. Also, for one of the practices, I'm just going to like straight up do one of the homework problems with y'all. So hopefully that will be a helpful thing and make it like less stressful. But any kind of questions about our game plan or kind of what's going on or anything else before we jump into section proper? There it is, the sound of silence. Okay, so let's jump in and talk a little bit about redox chemistry and specifically about diatomic oxygen, O2 in the house. So when you did your first Lewis structure in Gen Chem for O2, you did her with a double bond and 2 lone pairs on each. Each has a full octet. And when we are thinking about oxidizing O2 in a lot of these reactions, we are actually going to be thinking about 1 electron oxidations, just like adding 1 electron at a time to the O2 molecule and seeing kind of how it changes. So one thing that is helpful for us to do is draw a single bond resonance structure of O2 where we homolytically break the bond. So it's like we break one of the bonds here and give 1 electron to each oxygen. And formal charge-wise, technically each one is still neutral. It's a valence of 6 minus 5 lone pair electrons minus 1 bond, so it's still neutral. But this, I think, is going to help us see where we place the electrons as we add 1 more on it and keep on going. So we do a 1 electron reduction here, and we get this species. So it's often abbreviated as O2 dot. And essentially one of the oxygens just gets a negative charge on it. So anytime we have a negative charge, we can think about hiding that with a little proton transfer. And a lot of how we'll see it in actual mechanisms is within the enzyme active site, something is going to go and protonate her because we typically don't like having free charges around. when we can help it with an enzyme. So we started our most oxidized level of O2 diatomic, and then we did our 1 electron reduction. And then if we added another electron and we go ahead and place one of the hydrogens on there for good, then we get to this species where one side is OH and the other side has O minus. And if we do another proton transfer on that, we get both sides being OH. So this HOOH is also called, or written as H2O2, and this is peroxide, hydrogen peroxide. And so peroxides and peroxy as a prefix is referring to this OO single bond, which is not super stable. And so we're going to talk about some reactions that involve this OO single bond with monooxygenases. And this one in the middle, I forgot to give her a name. She's called the superoxide radical, which, I don't know, it just feels kind of fierce. Then, if we do another 1 electron reduction at an H, we get down and we are going to be splitting this bond, actually. So what we get is 1 HO dot, a hydroxide radical, and 1 HO minus, a hydroxide, which we can do a proton transfer and get to water. So we have one of our oxygens fully reduced now. It's at the H2O level. And the other one, we can do one final 1 electron reduction, get it down to OH minus, proton transfer to H2O. So we go from our most oxidized form to the most reduced form down here with water. All of these species in the middle, we typically refer to as reactive oxygen species, or ROS, ROS. And ROS are fairly toxic. So they can do unwanted oxidations in places we don't want them. Like, what is a chemical structure within our body that we don't want messed with? Our DNA. And so if reactive oxygen species get to DNA, it can cause some issues. But we are going to be doing some of this chemistry, and I think getting more used to working with just single radicals. It's helpful to just kind of lay this out again. I know you saw it in lecture, but at least for me, when I was coming back to this material, this was something I didn't feel as comfortable with. So we have our O2 oxidation levels, and then commonly for the enzymes that we're talking about today, we are going to be oxidizing O2 either to H2O2 to peroxide, and that's going to be in total a 2 electron reduction. And this is what happens in FAD oxidases. Or we are going to be oxidizing O2 all the way to water in a 4 electron reduction, which is what happens in FAD monooxygenases. And the E cell value, like I know you probably haven't done reduction potentials in a minute from Gen Chem, it's positive 0.81 volts, which is just like a huge reduction potential over here. So she is going to be very thermodynamically favorable. The other thing I wanted to just bring up is, remember FAD? It's been a minute. So the biggest feature I wanted to remind you about is that FAD is a redox catalyst. So it is going to be regenerated in every reaction. So all of the FAD mechanisms can be split up into two half reactions. The first half reaction, we are going from FAD to FADH minus, so something is going to kind of charge up the FAD and reduce it. And then the second half is going to be regenerating FAD. And you cannot stop writing your mechanism until you reform FAD. You may form the product after step 1. And if you don't reform the FAD, you will lose 20 points. I really like the meme, the stream ends when FAD is regenerated. Like, you're not allowed to go. And then just remember the little cheer, the 1, 2, ready. FAD is a catalyst. NAD's used up. FAD is a catalyst. NAD's used up. So, if I am obnoxious enough, hopefully it will come to you during the exam, and you'll be like, FAD is a catalyst. NAD's used up. Dun, dun. So that was kind of the key features of FAD. You're reforming FAD. You have these 2 half reactions. And last time we did reductases. So all reductases do is they load up FAD with NADPH or NADH. So NADH reduces FAD to FADH minus, and then FADH minus reduces the substrate. I put FAD. I'm going to do FADH minus just to be real technical with it. And honestly, I was like, why? And I ended up asking Serenia about it. I was like, why even do this? Because here, really, FAD is doing the same exact thing that NADH or NADPH would do. Like, why not just do this? And so when I asked Serenia about it, she was like, valid question. And she said it in some ways has to do with some kind of compartmentalization. But also we can think about both NAD and FAD are doing redox chemistry, but FAD is really the specialist. Like, FAD can do really, really technical chemistry that we're going to see in section later today. And so, again, it's kind of like our like blunt force redox agent of NADPH or NADH reduces the FAD, and the expert kind of does its job. So it's really, I don't know if that actually clarifies anything, but it made it make sense more to me of like, yes, she can do exactly what NADH or NADPH can do, and she can do more. And then the focus of today is going to be on the and she can do more. So we had reductases last time. Any questions about this review before we jump into oxidases? And a hush fell over the silence. Slay. So, our second class of enzymes after the reductases are oxidases. And really, I'm just to give you some like meta things to think about. The way that I'm thinking about these enzymes, functions, and different types of enzymes is we are going to talk about what is their main purpose. Like, why do these exist? Then we're going to talk about their strategy in the first and second half reaction. And then we're going to talk about the mechanism. And I'm really trying to do my darndest with the color coding here to help try to like drive home motifs and patterns. And so I tried to be as consistent as I can with the color coding here. But, so we'll start off with like big picture. Why does an oxidase exist? Well, it exists to oxidize the substrate. Groundbreaking, I know. So when it does this oxidation, it is not incorporating a new oxygen from O2 into the product. That's going to be a kind of key feature of oxidases. They're doing an oxidation and they don't add an O from O2. Whereas when we get to monooxygenases, we will see that they do an oxidation and they add an O from O2. So that's kind of a key distinction, that this does not add an O from O2. We also do not need NADH or NADPH like a reductase would need. So these are kind of like features that it doesn't need. The oxidase is honestly, to me, kind of like the baseline model because she doesn't really bring anyone else to the party. The other kind of general feature of it is it generates H2O2 during the process of regenerating FAD. So it's going to be doing this 2-electron reduction of O2 to H2O2. So now with oxidases, we have two kind of primary examples to look at. And then on things like exams and homeworks and everything, we can introduce more, but these are going to be the kind of like classic categories that you will see. The first one is glucose oxidase. And glucose oxidase is starting with glucose and oxidizing it into gluconolactone. And so if we look at functional groups and oxidation level, we start off here with a hemiacetal. So it's an OR and an OH attached to the same carbon. And this carbon's at oxidation level 2 because we have 2 bonds to electronegative things. So we are going from this hemiacetal oxidation level 2 to over here, oh crap, we have an ester, oxidation level 3. Wow, so we went up oxidation levels, we did a redox reaction, and whoa, we oxidized it. Remember, if we have a cyclic ester, it's called a lactone, so that's a fun verbiage. But you don't really need to know the names. I like the names. I didn't used to. I used to hate the names. And I used to be like, God, they won't shut up with the names. And now I'm like, an oxocarbenium ion. Like, I'm really into the names. So, sorry. So, okay, the first type here, and this feels like a really classic oxidation, right? Like, it's very clearly oxidation level 2, very clearly oxidation level 3, and also very clearly, we did not add an oxygen, right? These are the same boys. So we oxidize this carbon here. The second big type and classic example of a F8A oxidase that we see is called MAO, monoamine oxidase. And if we look at it, it looks like a little concerning. So it takes a substrate like this, where there is a amine here at oxidation level 1, and it oxidizes that amine to an aldehyde at oxidation level 2. So we are oxidizing, so oxidase, sure. But if I were you, I'd be like, Colton, wait, we just said that we are not incorporating an oxygen in the product, and very clearly there is an oxygen right here. And then somehow a nitrogen boy has left. To which I'd say, student, that's a really, really valid observation, but what you're not seeing is that both the oxygens in O2 wound up in H2O2. They're right there. And where did this oxygen come from? Well, it came from a free water molecule that attacked. So FAD's job, and its main thing that she's doing here, is just trying to oxidize this primary amine to an imine, if you remember that functional group from Chem 17 here. And so really, it's kind of like oxidizing an alcohol to a carbonyl, but we're doing the nitrogen version of it here. We're doing an amine to an imine. And then once this amine is formed, one of the reactions that we learned last semester was the imine hydrolysis. And it's a reaction here that if we add water and an acid to an imine, we get out a carbonyl. And so overall, these processes kind of pair together, and it looks like we're doing something that's way more complicated because we are both oxidizing and we're doing this amine hydrolysis. And so that's why she gets like a really like fancy special term. We call her oxidative deamination. Can you say it with me? Oxidative deamination. Ooh. Yeah, I don't know. It feels kind of sultry. It feels like, ooh, expensive. But yeah, so she looks deceiving, but she's just FAD doing her oxidase thing, and then we do an amine hydrolysis. So this is the overview. So what is our strategy here? We are going to, in our first half reaction, use FAD to accept a hydride from the substrate directly. So oftentimes we are going to be done with our substrate really, really quickly in this reaction. But then remember, the stream doesn't end until FAD is regenerated. And so this is going to be the new part that really feels kind of substantial here of we need to regenerate FAD using our O2. So we are using O2 to oxidize FADH- back to FAD. And in the process, the O2 gets reduced. So that's a reduction, that's an oxidation. Redox. So let's talk through the mechanism here. I haven't really decided if I would like to do the overview first and then get into the arrows, or do the arrows and then the overview. It's kind of like, I feel like if I just talk through this, it's going to be a lot of me like blabbing my mouth, but like, it's kind of like describing a car when I could just show you a car, you know? But I do think this will be a really, really concise map to refer back to, especially as you're doing homework and practicing. So let's start off with glucose oxidase because she's a little bit simpler. And let's do the first half reaction here. So the first reaction, half reaction, is we are going to take a hydride from the substrate and push it onto FAD. So a general base comes along, and we're at the hemiacetal here in the glucose. And it is going to deprotonate the OH and let it push it down its electrons to make a carbonyl. So that's allowing us to make this double bond over here. And then in the process, we need to kick off this hydrogen with its electron, this hydride. And we are going to put it on the bottom of this nitrogen and push all the way up. And that's really, really similar. Like these arrows look very similar to NAD, pH, charging up FAD and the reductase mechanism. So these arrows are like pretty similar to what we've seen previously. Yeah, and oh my gosh, I even made it the same color. Who am I? Great. So we have done our first half reaction. And when we do this, ba-dam, we get out the product, gluconolactone. Are we done yet? The stream is still on because we've made a mess. We've made FADH minus. So now all of the rest of this nonsense is just about getting FADH minus back to FAD. So we've done the first reaction. For MAOs, they have another step here, which is getting rid of that imine and turning it into the carbonyl, but we'll get to that in a minute. So first half reaction, we're at FADH minus and we made our product. And now we have 4 steps here in reaction 2 of reforming FAD. So the first thing that we are going to do is we are going to do a 1 electron reduction of O2. So when we do that, we make our superoxide radical. Is that the right word? Superoxide radical. Yeah, it is. Which I don't know why, but that always gives like super nanny vibes to me. But I don't think of O2 as like a very strict figure. I think of it as like wine ant as a figure. But superoxide radical, here we are. So once we've done that, we only have 1 electron up top for our FAD, and we're at FADH dot. And then what we need to do is we need to push this dot down to the bottom. And when we are doing this, this is actually a resonance step because we are not doing anything other than moving around electrons by our NP orbitals. The thing that's kind of weird with it is we're doing all these single fishhook arrows to show the movement of 1 electron, whereas normally you're doing resonance arrow pushing with 2 electrons. And so these arrows kind of look a little bit weird. But what we do is we take the electrons, the 2 electrons that are in this pi bond right here, and one of them is going to combine with the radical up top and make a pi bond at the top, the like northeast corner over here. And then the other electron that was in that pi bond is going to go down south. And we are going to shift our FADH radical down to this bottom position. Okay. So we made the superoxide radical. We did resonance and pushed down our dot to the bottom of the FAD. And now they're going to kiss. When we do this, it's important that we add a proton transfer. Because essentially what we are doing, this is going to be the second electron reduction that happens. So we gave it 1 electron initially, and now we're giving it the other electron. And so we basically want it to look kind of like H2O2 here. And so we want it to have this OOH single bond. And you don't need to bother at this point with drawing all of the like bonds and lone pairs that we were doing over here in the O2. This was mostly to help explain that process because we are just going from O2 dot to, after a proton transfer, we just have OOH. And so just kind of like making that a little bit more explicit. So we've done our joining together of our FAD and our O2 with a 1 electron reduction, and we have our proton transfer. And when we do that, we tether the OOH to FAD. So it's now like locked in. So now we are close. We have something that looks like H2O2. We've done this reduction of O2, so FAD has ostensibly been oxidized. And so now to restore FAD, our final step is we are doing something that's basically like an elimination. So imagine this is a leaving group, and imagine this is the alpha position, the beta position, a beta hydrogen. We have a base come along and deprotonate the beta hydrogen, push in, make a double bond, and then it kicks off our leaving group, which is going to grab an H as it's going out the door. And when that happens, the thing that's being kicked off is OOH, that's grabbing another H. And so that's our H2O2. So when we do that, we get back to FAD. Now, one question that I had like, I forgot what, like in office hours or something, was like, can y'all do this where you draw a little like cycle here and go back to the FAD structure you drew initially? I think it's fierce. I think it's art. Um, I would never, like, if I'm grading, count off for they didn't redraw FAD and just drew an arrow back to the original FAD, because I'm like, it's the cycles, it's the catalyst. But I do think all of the answer keys want you to draw it again. So, like, to be safe, I would say just draw an arrow out and then draw out the full FAD structure. See, this is the thing. I couldn't even start to draw FAD again because it's so painful. I don't want to do that. Chemists are so lazy. But we actually do want you for the end to draw out the FAD structure. I'll ask if it's okay for them to draw an arrow like this, but I feel like it should be because it looks like, it just looks cooler. It looks nicer. And also for me, it's a really nice way to close the loop on FAD, you know, because cycles. I can't believe y'all are still here. I'm really like doing my darndest with the corny jokes today. And there have been no notes. There's been no dissent. There hasn't been a mutiny. So things might get bad if this goes unchecked, but. Any questions here on the glucose oxidase mechanism, and specifically this part is the newest part, the reaction to regenerating the FAD. And maybe just so you can see it with the labeled steps here. So reaction 1, we reduced FAD with the H- from the substrate. So kicking off the H- here. Step 2, we did a radical activation by giving a single electron to O2. We did radical resonance down, the house down boots. Then we joined FADH dot to O2 dot with a proton transfer and did this kind of nitrogen elimination of H2O2. And when I say nitrogen elimination, I mean an elimination where we're stealing a hydrogen from nitrogen. We're not getting rid of a nitrogen. Yeah. Well, if that is okay. So MAO enzymes, which I don't know, does anyone call it MAO or do they just do MAO? Was Chris saying MAO? For MAO enzymes, remember we said it's really doing an oxidation from here to here, and then it's doing an amine hydrolysis. And so basically, there are just 2 extra steps, which are this amine hydrolysis here that we have to do for MAOs. And so this amine hydrolysis is we need water to come in and attack the aminium, and then we are going to kick off ammonia here, or ammonium. So what that looks like, I mostly just drew out the first reaction here. But we are going to do the same first step of the substrate has a hydride that it kicks off and reduces FAD to FADH-. So here, the weird thing is you don't need a base to come deprotonate this, just because amines are better lone pair pushers. And also the amine, yeah, I'll just say amines are better lone pair pushers. So we can push in, make the double bond, CN double bond, and then the hydride comes up, and up, same as we saw in even like a reductase mechanism. From there, we have the FADH-, and then we do the whole reaction 2 thing of regenerating the FADH. And so I was just like, we have this, and it's the same as above. So makes the O2 radical, does the resonance, bada bing, bada bing. But then we are not done with this substrate. So now we have a nitrogen that has 4 bonds to it and a positive charge, and this is called an iminium. So an imine is the neutral form, the charged form is an iminium. And our Chem 27 version of amine hydrolysis looks like this. So we have a water come in, and the general base is going to deprotonate it to make a better nucleophile. The water is going to go and attack, and then we are going to have it go and grab a hydrogen from the general acid here. I'm missing one arrow, which is this one right here. Now, you might be like, Colton, you're doing the thing again where normally for carbonyl we would push up and then have a lone pair go and grab this. And I'm like, I hate that, but I'll do it. But here, I'm actually right. Because does this girl have a lone pair on her? A nitrogen with 4 bonds? No. So we have to draw it my way. I win now. Everything's coming up, Colton. But once we do this, we have made this tetrahedral intermediate structure where we have an OH and then we have an amine here. And the neutral version of this, if it's NH2, this is called a hemi like halfway there because we're halfway through the reaction. And then amine for like amine, a hemiaminal, which again, I said it last semester, but it just tickles me. The first time I heard this term from a TF, they said it in passing and they said, and then you form the hemiaminal. And I was just like, Gesundheit. That's an involuntary utterance. Like, y'all are getting really too comfortable with this. I'm going to start a fight. And so now every time I see it, I name her. So we make our little hemiaminal-like girl. And we're halfway there, so we finish the reaction by deprotonating the OH, pushing down to make a carbonyl, and then protonating our NH3 as it leaves. And so, whoop, 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 I didn't draw the other one. The other thing that we get kicked off is NH4+. So with MAO mechanisms, we have to do this whole journey, and we have to do this whole journey of regenerating the FAD. So there's kind of just a lot to write. Cool. Any questions on MAO reactions? Okay. Well, let's try question 3 on your homework. So this is a mechanism here. And I actually moved it to the front page to give me more space to write, just to help with layout and things. So we need to do investigative journalism anytime FAD is involved. We have to be like, okay, what reaction's going on? And yes, this is the practice for the oxidase enzymes. But how do we know that this is an oxidase reaction just by looking at it? At this point, I will be asking for participation from anyone in the chat or unmute. What are some hints that we are doing an oxidase mechanism here? And then also, what are some hints for like which oxidase mechanism we're doing? Are we doing a classic one or are we doing a MAO?
Is it that we're doing an oxidase mechanism because we have like the oxygen molecule? And then is there a hint that it's the like regular one because we produce hydrogen peroxide?
So you are like right around it. The thing is, we haven't talked about the third type of enzyme yet, which also uses O2. And so like seeing an O2 here would narrow it down to either an oxidase or a monooxygenase. And the thing that's going to determine which one it is the byproduct here. So if we go from O2 to H2O2, like you were saying, that is going to be like our tip off of, hey, it's an oxidase. What else is tipping us off that this is an oxidase? Or any details about which type of oxidase we're doing?
I feel like it's the MAO because you're getting rid of NH3.
Slay. Yeah. So we see that we are forming, and also my pen just stopped working, which is really annoying. I don't want to have to like restart everything. I'm gonna like close it really quick and then try to reopen it. Oh. She said, let me update. Are you good? Can I use my pen? Yes. So, our hints here. Oh, God. What's going on? So we have O2 going to H2O2. That's classic oxidase. And then the other thing is we see that we are going from a carbon here at oxidation level 1 to oxidation level 2. So we are doing an oxidation into carbon. And then our tip-off that, and I'll put oxidase here. Our tip-off that we are doing now is we went from a nitrogen, a carbon attached to a nitrogen that was oxidized, and suddenly we have a carbonyl in the product. Likewise, we see this H2O. So we know that it's probably going to be likely that this O from H2O is going to wind up being this O that's incorporated into the molecule. Because for an oxidase, the O never comes from O2. Amazing. So now let's do this long, tedious mechanism where we're going to draw the structure of FAD so many damn times. So sorry. Ooh. I really try not to curse in front of y'all, but like, here we are. Okay, so FAD. We draw the 3 rings. The left ring is boring. The middle ring has top and bottom nitrogens. And the bottom ring has like north and southeast nitrogens. So we have 3 rings. The left one's straight up a benzene, and we put 2 methyls on it. Then the middle one, we need to connect the top up to a squiggle, and we call it FAD. And then we need diagonal bonds here with these 2 nitrogen carbons. And then lastly, we need to add a couple of carbonyls and a hydrogen. That's our FAD. And to be so honest with y'all, I'm going to draw that exactly once for the whole day. No. If it lets me copy it. So, what we're going to start with, and I'm going to be lazy and not draw the whole structure. On the piece that you should actually draw the whole structure for this. But I'm going to abbreviate this as R, CO2 minus, and then we have NH3 plus, and then the other thing that we have on dash here is a hydrogen. So with this in mind, we know that we need to move the hydrogen, the hydride here, from our substrate onto FAD. So let's do that. So we are going to get a general base in here. It's going to deprotonate this nitrogen so that we can push down, make a double bond, and then we are going to hit off a hydrogen onto our FAD. So this is our reaction 1, and this is our step 1. From here, we now are FADH minus, and so I'm going to do some rearrangement of these. So the top one has a lone pair nitrogen. We've added a hydrogen on the bottom, and our double bonds moved up to the middle. And then we have a couple of things. So I'm going to suggestively kind of write this in a couple of ways. Give me a moment. So we have our FADH minus that was created here. And then we also have our iminium that we just created. So now at this point, we go on separate journeys. So I'm going to finish off the product, and then we will come back to our FADH minus, because again, the stream can't end until we are done with that. So now at this point, a water comes in with a little general base, and we have a little general acid down here. The base deprotonates the water so that the water can do the attack of the imine or iminium. Then we're going to push up and grab a hydrogen. And that is going to, and this was our step 1B here, the kind of additional step for an MAO. That is going to make CO2 minus. We now have an OH that is added. And then we have an NH3 plus. And then from here, we're going to enlist our general acid-base friends again. We are going to deprotonate the OH from our hemiaminal intermediate. Push down, make a carbonyl. And then we are going to kick off our ammonia as an ammonium. And then here we generate our product. So again, if you only draw this and don't regenerate FAD, minus 15 points on the exam. No, we don't do that. You can get all the points. So let's now turn our attention to FAD and be like, we've made the mess, now we have to clean it up. So now we do step 2 of our reaction. Our step 2 is that we need to give an electron void to a diatomic oxygen to make our superoxide radical. So now, from this, we now have FDH dot. And then we have an O2 dot. And the FADH dot is actually neutral with this. Like she's just chilling. Because that nitrogen, again, formal charge, or valence is 5. It has 1 lone pair and a radical, so minus 3 lone pair electrons, minus 2 bonds. She's neutral. But we need to push our resonance down now. So we're going to have 1 electron from the double bond combine with our dot, and then take the other electron in the double bond and push it down south. This was our step 3. Okay, so now at step 4, this is when we really start cooking. Boop. So now we have a dot down here. We have an O2 dot. And then they kiss, a little bond. This is the one where we need to be sure to do our special little reduction. Proton transfer, as we are doing our reduction. So this is the one that had the 1 electron reduction. The other stuff that was the 1 electron reduction was this one where we gave an electron to the O2. And so now we get to the end game in a very kind of Thanos way. Peroxide says, I am inevitable. So it's okay if your bond looks long. We won't sue you. But now we are at the right oxidation level, and we need to get that off here. So we need a base and a general acid. So we are going to do this kind of elimination on this nitrogen. So we deprotonate, fold down, grab an H, and then protonate it as it's leaving. When we do that, we regenerate. FAD, and we also spit out an H2O2. And then a question in the chat was, can we collapse steps 3 and 4, or do we have to do them as separate? That's a great question. Let me check. Like, I mean, I feel very comfortable with, like, let's collapse them. Let's make them one. And in lecture, they might have done that. So So in lecture, I think you showed it as 2. And let me also like check the answer key. Like it is valid and fine and good chemistry. And I can show you how to do it in one step if you really want. Why did I say that like that was enticing? Like I just mean I'll draw it. So for P set 6 key, how did they draw it? They drew it as one step. They collapsed it. So if we wanted to do this all in one, we could do 4. Steps 3 and 4 together look like very, very similar. And then you would just have, instead of it going down to carbon, it go and meet up with O2. And to be so honest, if I was you, I would do this. And I would do this just so you don't have to draw FAD again on the exam when you can't copy and paste. Yeah. So that's kind of our abbreviation of these 2 steps. It combines the resonance, and I'll also put a double-headed arrow here for that. But yeah, this is a really classic monoamine oxidase, MAO. So this was our MAO hint. Would it be helpful for me to put the highlighting on this, or are you like, I'm good? Actually, we're already at 6:52, so I might just not highlight it. But as on your own, do a like paint by numbers, color, make it match. Slide. Okay, so now, any questions on oxidases before we go to the last major FAD type of the monooxygenase? Okay. So, monooxygenases, zooming out, the purpose. Why do they exist? They exist to do a 2-electron oxidation of a substrate that also adds an oxygen. Which again, the MAO seemed like it was doing that, but the FAD and the O2 was not actually adding it directly. It was a water that came in later. So here, the oxygen that we are adding in our monooxygenase comes from O2. The other kind of key feature of monooxygenase is we are going to bring back in NADH or NADPH to activate our FAD in the first step. So, doing oxidation by adding an oxygen, monooxygen, adding 1 oxygen, monooxygen. Our strategy, step 1, we reduce FAD with NADH or NADPH. And then step 2, we are going to regenerate FAD with O2. In the process, we're going to now generate water instead of H2O2. So that's going to be a big difference, that monooxygenases generate water, which only has 1 oxygen, because where's the other oxygen? Well, it was incorporated into the substrate. So we do, in our second reaction, regeneration of O2, and we're going to incorporate an oxygen into the product somewhere in step 2. Now the setup for this, our color coding shows us some colors we've seen before. There are a lot of things that are really, really similar to oxidases and reductases. So like this first step is the exact same as a reductase mechanism, where we are going to use NADH or NADPH to reduce FAD to FADH minus. And then in reaction 2, literally all of these steps are exactly the same as the oxidase steps. Verbatim, same arrows, kaput. The only variable step is this one right here before the final elimination, where we use the peroxide to somehow add an oxygen to the substrate. And this one is going to have a lot of variability, and there are lots of different ways to do it. And so we'll talk about a few of them here. So, there are two main kind of examples or types, and really I feel like I needed a better way to word this. We call these flavin monooxygenases FMOs, and then we're also going to teach you about one special subtype of FMO that's called the Bayer-Villiger monooxygenase, or a BVMO. And it's not exactly like for the oxidases, we have a classic oxidase and then we have a MAO. The Bayer-Villiger really is this exact same structure. It's just going to be doing a weirder step 5 that we want to give a little bit extra love and attention to, because y'all have not really seen a classic OChem 2 treatment. Because really this class is more of a biochem class that does curved arrows, you know? But with that, let's look at a classic flavin monooxygenase. And so one type of monooxygenases, or one common product type that we will see, is making a structure called an N-oxide. And an N-oxide is literally just, we have an oxygen on a nitrogen. And they can do this kind of like fierce thing where you trap two charges on it. Like a positive charge on nitrogen, because this nitrogen has 4 bonds, can't be deprotonated, and negative charge on oxygen. But then since the positive and negative are right next door, it's actually not that unstable. Kind of weird. If you took 17 last semester, this is kind of similar to like an ylid, where we had like an RC, or actually, I'm going to do it this way. PPH3 plus and a minus on the carbon. So it's a very similar thing here, where it technically is an ylid, but we call it an N-oxide. So we use FAD in the structure. We are using up a NADPH. NAD is used up. And then we generate an H2O. So these are our kind of investigative journalism hints. So let's do the mechanism. We said that we need to start off by loading up FAD with a hydride from NADH or NADPH. In this case, we're using NADPH. So we push up to the stars and add a hydride onto the bottom of FAD and push up and up. Then we get an NADP plus kicked off, which you should draw the structure. I just didn't to save space, so draw the structure, please. Sorry. I hate it. Then we act as if we are doing the same exact thing that we did last time. So we are at FADH minus. We go and give an electron to O2. Then after that, we do, we're at FADH dot, we do resonance and push it down. And then we join together the FADH dot with the radical at the bottom and the O2 radical. And we get, after a proton transfer, to the same peroxide intermediate here, this FAD peroxide. Yeah, I just uploaded the PDF like 2 minutes before the session start time, so apologies. Cool. And again, you can combine these into one step, and I would probably recommend that you do that so you don't have to draw as much. So steps 3 and 4 can be combined. Okay, so now step 5 of the reaction 2, where we are regenerating FAD. This is where we do our like final reduction bit, and it's also where we add we add an oxygen onto the substrate. So in this case, what's going to happen is our substrate, the nitrogen, it's going to take its lone pair, and it is going to attack the far oxygen. So it is going to be attacking the sigma star OO antibonding orbital, breaking this sigma bond between the two oxygens, and then we are going to push electrons off onto this O. So if we trace where we did our reductions, if we generate H2O, we're doing in total 4 electrons worth of reduction. So this is a 1 electron reduction we said. This we said was a 1 electron reduction. And this right here, giving the electrons both to this oxygen, that is the 2 electron reduction that's happening. So again, this step is going to be different for almost every different monooxygenase that you see. And this is just going to be one of them. But once you do that, what you're left with here, ooh, I made a mistake. I'm so sorry. Again, it's my first time making these lessons. Oh wait, no, I didn't make a mistake. I was like, wait, this should just go and grab a hydrogen from an acid, which we could draw it that way. We totally could. But I covered my butt because I put a proton transfer. And so lots of things can happen in a proton transfer. Really, only two things can happen, protonations and deprotonations. But the thing that we needed to happen happened in the proton transfer. So with that, we generate our product. But we're not done yet. The product is a distraction. The stream ends when what? FAD is regenerated. And here we are really, really close. So again, we had OH in the original, and we did an elimination with a hydrogen off this nitrogen. And we're doing the exact same arrows here, but now the only dangly bit that we have is an OH, not an OOH. So when we come and do this elimination with a general acid and base, we spit off water, and then we reform our FAD. And again, isn't that a fierce little cycle? Don't you just want to, like, do chemistry all the time? Like, I don't know. So any question on this N-oxide FMO, monooxygenase mechanism? Because this is going to be kind of our platonic ideal for it. And then we're going to swap out step 5 here with a couple of different things that we can do. Maybe I'll do it so you can also see the labeled steps and just kind of compare and contrast. Okay. So now, let's do another one. And this is one you haven't seen before. This is one that Colton is bringing out of the depths of hell to torment you with. But just to give you another example. So there is a monooxygenase called squalene epoxidase. So squalene is this girl. She is long and fierce, and you're going to learn about her in a later lecture, the isoprene terpene lecture. We don't care about all of her right now. So I'm just going to abbreviate this little end over here as this. So squalene epoxidase, what she does is takes our squalene girl and takes one of our alkenes and turns it into an epoxide. Does this satisfy our monooxygenase things that we expect? Well, one, we're generating an H2O from it, so yeah. Second, we are incorporating an oxygen, yeah. And then it's kind of weird with the accounting of it, but we are technically doing an oxidation here when we go from the alkene to an epoxide. Yeah, there are a couple ways to think about it. One way to think about an alkene is you have one carbon at oxidation level 1, one carbon at oxidation level 0, and then here both of them are at oxidation level 1. But to be so honest, I'm not going to get mired in the details of that because also this is a bonus example just to show you a different step 5. So every single part of this mechanism, all of this up until this, is exactly the same. So we do the same loading of it with NADPH, and then we do all of our FAD steps to get to our peroxide FAD. And now we are trying to get from an alkene to an epoxide. And so what we're going to do is a mechanism that's really, really similar to an epoxide forming mechanism that we saw in 17. So we are going to have the alkene come and attack this oxygen-oxygen sigma star and break that sigma star bond. But at the same time, we're going to have a base deprotonating here and allow the oxygen to attack back the antibonding orbital of the pi bond, so the pi star CC. And so you get this kind of fierce step where there are a lot of arrows happening at once. And especially these like acid-base things here, I think that makes it look a lot more frenetic. But fundamentally what we are doing is the alkene is attacking an O, and then the O is attacking right back to make our epoxide product. Then from here, we just finish it out the exact same way and generate FAD. So we are making a very different functional group, an epoxide here, versus a N-oxide. But the only step that is different is step 5. And so, again, on something like an exam, on a PSET, you might have to do something a little funky in a step 5. So, now that we've seen these with classic kind of flavin monooxygenases, let's introduce a random fact for now. Let's pivot and make this an OChem class again. So, we have the Bayer-Villiger oxidation. And actually I have a student right now at the University of Georgia that I'm tutoring for OChem 2, and she has her test that includes the Bayer-Villiger oxidation like this Wednesday. And so I've just been like doing that. I'm like, wow. So what the Bayer-Villiger oxidation is taking a ketone or aldehyde and oxidizing it to an ester, which I don't think I actually write the word ester on here, and I think I should. Ketone aldehyde. And what it uses to do this oxidation is a peroxy acid. So what a peroxy acid looks like is it's like a carboxylic acid, but we're going to add an OO bond, like peroxide, like we saw earlier today. So MCPBA is the classic. I think she's fierce. It's our R group on the peroxy acid for MCPBA is a benzene ring, and at the meta position we add a chlorine. So metachloroperoxy benzoic acid, MCPBA. Names. So this one, Bayer-Villiger, I imagine is like the SpongeBob meme, but normally the SpongeBob meme is I'm a head out, right? And oh, the top of the eye got chopped. So normally the SpongeBob meme is I'm a head out, but instead I imagine the armrests are carbons, and the Bayer-Villiger oxidation is like I'm gonna squeeze in. I'm just going to insert an oxygen in the middle here. And so it's kind of a weird little arrangement. But what we do is this is a peroxy acid, so acid's in the name. We protonate the carbonyl, and then we have the negative charge on our peroxy acid come and attack the carbonyl push up. The key step here, and the weird step, like this one is the one that kind of prepares for the main Bayer-Villiger step, but the key step is we are going to do a lone pair push, and instead of kicking off some like leaving group on this carbon, we're going to do a rearrangement. So we're going to push down, and then a methyl over here is going to shift over. And it could be a methyl, it could be any other alkyl group. So when we do that, our like MOs that we are doing, a lone pair on oxygen is being put into the sigma star. Ooh, I made another mistake. This should say sigma star CC. Because we are breaking the carbon-carbon bond between the carbon that's the tetrahedral intermediate and the carbon that's currently a methyl there. So when we put electrons into the antibonding orbital for this bond, that breaks the bond. And then we are using the electrons in that sigma. Wow, another typo, sigma CC. I don't know why I was trying to make a sigma CO. The electrons in that sigma CC bond to go and attack this oxygen, put electrons in the antibonding OO sigma orbital and break that off. So we push down, we shift over, and then we kick off this carboxylate now, which is actually a pretty good leaving group because it's stabilized by resonance. So when we do that, now our oxygen's kind of inserted between the carbon of the carbonyl and the methyl. And all we have to do is something in solution comes and deprotonates it. So if you were in a classic OChem 2 class, this would be one of like 60 reactions you'd learn in a unit on ketone aldehyde reactions. But why did we introduce this? Well, there is a flavor of monooxygenase called a Bayer-Villiger monooxygenase that we abbreviate as BVMOs. And they do this thing. They go from a ketone or aldehyde, and then they insert an oxygen in. I think one of your class notes went from a 6-membered ring to a 7-membered ring. And so just for variety, I've done one from a 5-membered ring to a 6-membered ring, just to show it out. So again, this is going to be the exact same as every other monooxygenase, starting from the NADPH or NADH and going all the way to this peroxyacid FAD. And then once we are at the peroxyacid FAD, what we are going to do is we are going to use the Bayer Villager as a template here. So what happens is we are going to deprotonate this at one of the far oxygen, this OH, and then have it attack the carbonyl. We will push up and then have the carbonyl grab an H. So what that is doing is it's basically combining these first two steps together and getting to our tetrahedral intermediate. Then, once we are at our tetrahedral intermediate, we've tethered our substrate onto the FAD, onto the enzyme. A general base is going to help this do a lone pair push down. We do a rearrangement from the carbon group, and then we break the OO bond. And so here we have it just grab a hydrogen from an acid, which I'm missing one more arrow there. So now, when we do that, we've generated our product that is this ester, this cyclic ester called a lactone, like gluconolactone. And then we still have our FAD that we have to regenerate. So we still do step 6. But again, all of this is to say the only thing changing is step 5 in every example. And all of these you had seen before, either in oxidases or in reductases. So again, these look really big and complicated, but they're made up of a lot of these components that repeat themselves. So with that, why don't we try out a mechanism together, a practice. So with this, we're having to do investigative journalism. And there's some information that we are not getting. One thing that we are not told in this is, do we have a side product? So let's do some investigative journalism here. Imagine you didn't know this was supposed to be the monooxygenase practice. What are some of our tip-offs that we are doing a monooxygenase?
The reaction requires FAD and oxygen.
Yeah, well, and that gets us down to monooxygenase and oxidase. So then, how do we tell? I see some adding O's. Yes, so we have an O that is added in our product. And that's probably going to be our biggest tip-off, that we add an O. Now remember, the MAO, we added an O, but then this was also done in an oxidation where we went from an amine to a carbonyl. And this amine to a carbonyl is the classic MAO thing. So if we are not going from directly an amine to a carbonyl, then we are likely going to be in the monooxygenase camp. And then more than that, what is this? The name of this, where we have an oxygen attached to the nitrogen. This one, we don't have the charges trapped on it because this is not a tertiary amine. But this is still an N oxide, which is a really common product of a monooxygenase here. So these are our tip-offs that we are doing an FMO reaction. So if we are doing an FMO, we've incorporated one oxygen in the OH here in our product. So what is our side product that we get? So we're using up an O2. One of the oxygens goes here. So what else should we have as a side product?
Water.
Water. Yeah. So we need something with one more oxygen. And it's going to be Miss Water. Okay, Slay. So, with this, let's jump in. And do I still have the FAD? Yes, I do. I still have it. Copy and pasted. So. Oh, I might be super lazy here. We'll see. So we have our FAD. And then what am I going to do? I'm going to abbreviate everything again because chemists are what? Lazy. Oh, wait, what am I doing? I was about to draw this. But why is that a silly thing for a monooxygenase, Colton? Why would it be silly at the very start to draw the substrate? Well, is the substrate what loads up the FAD? Nah, the NADPH or NADH is. So, in this reaction, we would expect, even if it's not given here, that we have an NADPH going to an NADP+. And again, it's because we know it's monooxygenase. So we can supply the NADH here. You have no way of knowing which one it is, so just choose one. So I'm going to choose NADH. So NADH, we start off with the 2 hydrogens up top, but we don't have our aromatic ring. And what we are going to do is we are going to push N up and kick off a hydride. And oops, I need to just fix my double bonds here and my copy and paste. There we go. And then when we kick off the hydride, we're going to have an attack at the bottom of the FAD and push all the way up. So from here, what we get is FADH minus and we get our NAD plus. Okay, so we've done our step 1 and reaction number 1. NAD is used up. So now we start the process of reaction 2. So our step 2 here is we are going to give a radical to an O2. And then when we do that, we're going to get FADH dot. And now I'm going to combine 3 and 4 because that is more compact. So we are going to push the radical up top down. And then with the other electron that was in this pi bond, we're going to have it come out and combine with our O2 radical. And we're going to do this with a proton transfer to make our peroxy FADH. Long bond, we won't sue ya. Okay. I think that's good. And then we don't need the O2 anymore. So now we do our step 5. Remember, step 5 is our interesting step. So at this point, we need to get rid of our oxygen and put it on the product. So I'm going to abbreviate this as H2N R. No, actually I'm going to do it even more. I'm going to do it as H2N. No, is that crazy? I mean, that's a little. H2N R. So I'm going to have my H2N R. And then we are going to have the nitrogen straight up attack our OH down here. And when we do that, we are going to kick off our FAD molecule and let it grab a hydrogen from a general acid here. So the oxidation states are a little bit different from the one we did before. So like we did a proton transfer in the other one, but as long as you do a proton transfer or use general acid and base to cover your bases here, we are going to get to the same place. So what I want for the product that we get out of this is I want it to be HN, and I've added an OH on it. So to do that, I'm going to make sure to put a proton transfer here. Alternatively, you could have written this out as NHH and used a base here to deprotonate this, and then had the arrow come from this. Either one is fine. Like we're all doing different abbreviations of the same thing. So I just added the proton transfer on it. And now we can do our final step here with our in elimination. So we're going to grab an H, form an alkene, and then kick off this water. And a fierce little regeneration. And as we are doing that, we are kicking off a water. And that was step 6. Yeah, for some reason this whole process is so less daunting to me when I number like reaction 1 and reaction 2, and then when I number the sub-steps. Suddenly it goes from like a C of crazy to, oh yes, I'm in step 2 of 6. I know where I'm going. Everything is fine. Okay. Any questions on her? So with our monooxygenase here, this is our last flavin reaction, and this is really our last new reaction, I would say, for the Unit 2 main content. Because the first step of glycolysis is just an ATP mechanism. So now we are going to do a hard pivot switch gears. Our hard pivot switch gears is I'm going to spend like 10-ish minutes talking about sugars. Because we want to start talking about glucose. To be so honest, I think I'm just going to skip this. This is literally, I was just going to do a recap of 2 pages in the lecture notes that was like, sugars. They can be linear or we can cyclize them. And then this anomeric effect of stabilizing the alpha anomer. I would say for this, it's less important. And if we have time for the next section, I'll kind of come back to this. But I would say, I'll even tell you the pages of lecture notes that it is on that I just like was like, no. Page 18. Literally just page 18 of lecture notes. Maybe one thing I will say, because I do have a question down here, is here we have glucose, and what we need is we need to determine the alpha anomer or the beta anomer. So anomers are just our special name for cyclic diastereomers that we have here in the glucose molecule. One way that we can tell that this is glucose is fierce because she's the most stable. So in glucose, all of our hydroxyl groups are equatorial, except for potentially this one. Now, the anomeric carbon is the carbon that is most interesting on a glucose or on a sugar molecule. And it is the carbon that is the hemiacetal carbon. So this is the anomeric carbon. And it's the hemiacetal. So there is actually like a technical terminology for all these sugars, and I'm about to tell you something that's not true for every sugar, but it is true for glucose. So for glucose, the alpha anomer puts the OH axial, and the beta anomer puts the OH equatorial. And again, I think alpha axial is kind of easier to remember. So this one right here in our anomeric carbon, it has the OH axial, so this is our alpha anomer. And then over here on the right, we have our beta anomer here. So I will just say that this is one that when we go from a straight chain sugar to cyclize into a ring, we could form this alpha one, or we could form this beta one. And the thing that we see is the beta one is about 60%, and the alpha one is about 40%. And you might be like, oh, okay, that makes sense. Equatorial is more stable, right? So it would prefer it in the equatorial more. And that is true. But really, if we prefer it in equatorial and we have each choice, why isn't it like 90%, 10%? Why do we have so much alpha anomer? And the reason for this is because of something called the anomeric effect, which I'm going to talk one more minute about the anomeric effect and then I'll move on. And this is not the answer to the second part of the question down here. I'm just drawing it here because that's where I was when I started talking about it. So when we have the OH in the axial position, we get something interesting that happens with our antibonding orbitals. So we know our bonding molecular orbital is here where the actual bond is, but the anti-bonding molecular orbital is kind of like, what if we did an out of phase overlap here of our orbitals where like the shaded and dashed didn't line up. So this is our sigma star carbon oxygen orbital, and it's unfilled for a reaction, or for this structure here where we have a single bond present. And what happens is we can think about the lone pairs on this oxygen occupying an axial and equatorial position, just like two substituents would on the oxygen, because we know this oxygen's tetrahedral, and we know that in a chair it's going to have an axial position and an equatorial position. So what happens is the lone pair that's axial here, it is going to be lined up with this antibonding orbital. So the lone pair on oxygen can donate into the sigma star carbon oxygen antibonding orbital. Whoa. Okay, that feels kind of like, what does this all mean? Basically, this donation is stabilizing. And it's kind of like hyperconjugation. So we said, for example, last term, that if we had a carbocation, we had like an empty p orbital, then the more neighboring hydrogens that we have, the more of this hyperconjugation there would be, where all of these neighbor CH bonds can donate in, bloop, 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 and so on, and stabilize the carbocation. And this is why tertiary carbocations are more stable than secondary, more stable than primary, that idea of hyperconjugation. The anomeric effect here is really like that hyperconjugation stabilization, but it's just with a lone pair next door. Now, to be sure, this is not resonance. This is not as strong of a sharing of electrons as resonance, but it is a stabilizing electrostatic effect, and it's what accounts for this being as high as it is for the alpha anomer. Increased because of the anomeric effect. which stabilizes the antibonding orbital. So that's maybe the biggest thing that I wanted to say here on the sugar conformation. And with that, to be so honest, I'm gonna go like 7 minutes beyond my normal deadline of 7:30 just to do an intro to glycolysis. It won't be super long. I don't have that much to actually say because all of it's written on here. But I did want to touch on a few things. And if you need to head out, totally fine. But let me do this last little bit. So, you've seen glucose metabolism in bio classes ever since probably like 9th grade bio. You've seen this process happen. And really, up until now, I feel like there has been a lot of hand waving as to like, how does this get done? How do we take a glucose and get out ATP, our energy for the cell, really? And now that you've learned this organic chemistry and this biochemistry and these cofactors, you actually have the tools to understand the nuts and bolts of how do we do this. So we know that ATP is generated via NADH and FADH2 and the electron transport chain. And we'll get to that later. But like as a biology fact, this is where we know we are making the ATP in large chunks, large quantities. And so in our metabolism of glucose, we need to do some, I said oxidize. We need to reduce NAD plus and FAD. We need to load them up with electrons so that they can drop off their electrons and protons and the electron transport chain, generate a proton gradient, blah, blah, blah. But we are going to be doing a lot of reductions here. The other thing is we need to dispose of the 6 carbons in glucose. Because essentially, after we've extracted all the electrons out of them, they're a byproduct. We don't care about her. And the way that we dispose of carbons, once we've fully oxidized them, taken all their electrons, is as CO2, as a gas here. So in glycolysis, in working towards these chemical goals of reducing NAD and FAD and then disposing of the carbon as CO2s, our goals, chemically, are we want to chop up glucose, which is 6 carbons, into 2 3-carbon units, and we want to oxidize those carbons from our original glucose into pyruvates. So if we start off with our glucose here, glucose and sugars more broadly, they are really unique among all the like biomolecules because really it's the only like molecule, sugars, and then some of these intermediates here that we're going to talk about in the sugar metabolism that have carbons at oxidation level 2. And really it's this carbon right here, that's the hemiacetal. In our cyclization, decyclization, we know that this is actually standing in for an aldehyde over here. So that's what this CHO abbreviation is. So ketones and aldehydes, outside of like sugar metabolism, you are not going to see them a ton. And they are really the defining feature chemically of sugars. They have something at oxidation level 2, and then they have a bunch of alcohols. So in each of these carbons, each carbon is connected to at least 1 oxygen. 5 of them are at oxidation level 1, and then 1 of them is at oxidation level 2 in glucose. But then by the time that we get to 2 pyruvate molecules, we've basically made them into these 2 3-carbon chunks that are identical, which is really helpful for like redundancy. Like we don't have to have double the amount of enzymes to break up 2 different things. We can feed both of these into the same next steps. But we have 1 carbon on each of them, so 2 total that are at oxidation level 3. We have 2 carbons at oxidation level 2, and then we have 2 carbons that are oxidation level, technically this is 0, so I shouldn't even put a 1 there. So in total, if we added up all the oxidation levels over here, we had 5 1s and 1 2, so that's a total of 7. But over here we have 2 3s, 2 2s, and 0. So that's 6 plus 4. This is 10. So we kind of went up 3 oxidation levels total. Which I know that's kind of a weird math for like bookkeeping of our oxidations. But again, I think it's just driving the point that we are trying to oxidize this. And eventually we are trying to get every carbon to oxidation level 4. So this does a lot of heavy lifting to help get us there. So glycolysis, we're not going to go into a ton of detail about it. And like, honestly, this is just here as a reference. You do not need to know all of this at all. Even though I think it's fierce to know it. Glycolysis is split up into 2 phases. The first phase we call the preparation phase, where we are having to spend money to make money. We are putting in some ATPs here, and spending that ATP. And what we are trying to do is first get to this structure, fructose 1,6-bisphosphate. And the thing that's really fierce about her is she looks nearly symmetrical, right? She looks like we can almost completely divide her in 2. Whereas glucose, if we look at our glucose up here, she's a little cattywampus. Like, she doesn't look exactly the same on both sides. So we get to this fructose 1,6-bisphosphate, and then we cut her in half and get out 2 GAP molecules, glyceraldehyde 3-phosphate. So really, the goal of this first phase is to get to 2 3-carbon chunks. We are doing check mark to this chemical goal of chop up the glucose into 2 3-carbon chunks. And that's our preparation phase, where we're investing ATP, and then we are lysing it and cutting it in 2. A lysis phase, investment and lysis. And then the second half is our payoff phase. So in the payoff phase, we get money. We get ATP out. And we are doing all of these steps twice because we do it for each GAP molecule. So we are getting out ATP, but what else are we getting out? We're getting out some NADHs because we are doing some oxidations now. So with this, overall, you are getting a net 2 ATP and a net 2 NADH that are generated from glycolysis here. The delta G overall for this process is like -20, so it's like multiple ATPs worth. And so it's very like thermodynamically favorable. And at this point, we're not going to go into any more detail. We're going to talk a lot more about glucose on Thursday in lecture 7, which is not test 2 content to my knowledge. But the last thing to leave off on is because we don't want you to just like blindly memorize glycolysis like in a traditional biochem classes. So like in a biochem class at most universities and in medical school, honestly, you're going to have all these structures and all these enzymes memorized, like at least the intermediates and especially the regulatory steps. But we're wanting you to think through the chemistry of it. So right now, at least, and at this point in your academic career, instead of memorizing it blindly, we are going to try to think smarter, not harder. And we are going to talk about classes of enzymes that appear in metabolism. And the first class, I've highlighted up here in purple. These are called kinases. So kinases are enzymes that use ATP to add a phosphate onto something. So over here we see we added a phosphate on from ATP, and we got from glucose to glucose 6-phosphate. Then over here we had another one, phosphofructokinase, and it added on a second phosphate from ATP. So we've added on 2 phosphates. The kinases in step 2 in the payoff phase are the ones that make ATP. So we can also call something that generates ATP a kinase if you generate ATP by putting a phosphate onto a DP. But the mechanism for these two that are in the first half of glycolysis, these 2 kinases, the first one's hexokinase, taking glucose to glucose 6-phosphate. And then the second one is phosphofructokinase, or PFK. And it takes us from fructose 6-phosphate to fructose 1,6-bisphosphate. The mechanisms are like straight up something that we could have given you in lecture 4 or section 4. So we deprotonate at one of the oxygens, and then we have it attack the gamma phosphorus and ATP. and we've added a phosphate group. There's also a magnesium that's associated with it that kinetically activates these. But yeah, so this is just kind of like, yes, do you remember ATP? She's showing up again. So now you know the mechanism of 2 out of the 10 steps of glycolysis. And again, if you want a little jump scare, there's the full thing. Whoa, isn't it so cool? But we don't know about that. We only know about kinases, ATP. So that's all I have to tell you about sugar and glycolysis for now. Next week I'll probably have some more remarks gathered. But thank you for coming to section. Thank you for staying a little bit longer. We also started a little bit late, so I feel not as bad going a little bit over. And then if we have time, maybe I'll talk a little bit about these next time. But honestly, it's 1 page of lecture notes, so here it is. Okay, from here, I will stop the recording. Goodbye, recording.